For Mechanical Engineering 223, our group was assigned a project to test our knowledge of Arduino programming and design principles. Our group consisted of Trent Dalton, David Waters, and Will Segmiller. The goal of this project was to create and program an electromechanical device that would measure the length of filament used by the MakerBot. The MakerBot Replicator 2 3D printer uses filament with a diameter of 1.75 millimeters. This filament is stored on the back of the MakerBot in a large spool. So any device we designed would need to be small, as this is where we want to mount our device. An Arduino board is a programmable microcontroller that can be used to prototype interactive electronic devices. With one, we can control an electronic sensor. Using this sensor, we can detect the length of filament the MakerBot uses. The sensor we decided to use is called a rotary encoder. This is a device that detects rotation and can spin an unlimited number of times, unlike simpler components like a potentiometer. When its shaft is turned, one rotating disc rotates against a stationary disc. Both discs have alternating regions of conductive surfaces and insulating surfaces. When two conductive surfaces make contact, the rotary encoder detects the connection, and for each rotation of the shaft, there are 24 connections made in our specific rotary encoder. The design we came up with uses two separate components. The first is this wheel. The hole in the center of the wheel fits over the shaft of the rotary encoder. The flat side of the hole corresponds with the flat in the shaft of the encoder. This means that when the wheel is turned, it will also cause the encoder shaft to turn. The filament is to be pulled along the circumference of the wheel, where it will be held in place by the groove. The large structure in the center of the base, here, holds the rotary encoder securely in place, and the two smaller structures off to the side guide the filament and hold it in place against the wheel. This is what our final design looks like when assembled. The wires extending from the top of the rotary encoder go to the Arduino board, while the device itself is held against the back of the MakerBot. Ultimately, the device will be bolted on, but for this test we simply taped it in. Here we see our device in place and ready to measure. It fits into the small available space very neatly and does not interfere with the operation of the MakerBot in the slightest. This is a video of our device producing measurements while the MakerBot runs a project. What you see now is the serial monitor of the Arduino updating the measured length of the filament in centimeters. As you can see, the wheel turns very slowly. It is impossible to see its rotation without some reference, which is why we placed the dark marks around the rim of the wheel. This is the MakerBot itself, working on its project. As you can see, it uses filament at a very slow rate. As we go back to the serial monitor, we can see that even a small print job like this one can use a surprising amount of filament. At the beginning of our project, we decided on two specific needs that our device needed to fulfill. First, it needed to measure the length of filament used by the MakerBot, and our goal was to achieve an accuracy of 98% or more. This means that with a 1000 centimeter print job, we would only lose or gain 20 centimeters. We intended to test this by running a test piece of filament through the system and seeing if it was within our tolerances. We also wanted the device to require limited human interaction to operate. We wanted it to work so that after its initial setup, it did not require an operator to work properly. With regards to our first goal, we achieved better than expected accuracy. Though our goal was to achieve 98% accuracy, we actually achieved 99.8% accuracy, only gaining 0.14 centimeters over 147. As for our second goal, the only thing the operator needs to do is turn on the serial monitor. Once that is done, the device will run on its own. We learned many important things in this project. We discovered that with a project of any scope, one person cannot do everything and that all team members must be involved. We also discovered that it is important to have specific tasks outlined for each person. This promotes rapid completion of assignments and reduces risk of miscommunication. And, as has been demonstrated time and time again, no job is complete until the paperwork is done.